Today's lesson is on sequences and series. First of all, let's understand the difference between a sequence and a series. A sequence is just a list of numbers, like 2, comma 5, comma 8, comma 11. You see how they're separated by commas? They can have a beginning and an end, like maybe the sequence might only be 7 numbers, or they can go on forever. Now with series, this is the sum of a list of numbers. For example, 2 plus 5 plus 8. So the biggest difference is sequences, I always think commas, and for a series, I always think addition. Sequences and series are super useful in the real world. For example, you can maybe have an auditorium and you're trying to look at how many seats are in each row. And maybe you notice the first row has 8 and then the next one 10 and then 12. And you establish a pattern that each row is 2 seats longer. So maybe you want to figure out how many seats are in the 12th row or the 80th row, if it's that big, or maybe how many seats are there all together in the first 10 rows, then you would use a series. So very, very useful. Even let's say you had this right here. This could be defined as 0.7 plus 0.07 plus 0.007 to infinity. So we'll be looking at things like that as well in this chapter. And we can actually see exactly why this equals 7 over 9. In this chapter, you're going to learn some formulas, and it's just going to be a little bit different way of thinking. We're used to using function notation, where we see things written like y equals 2x minus 1, or f of x equals 2x minus 1. You might also pick some x values, populate a table by plugging in x here, and you'd get what? Negative 4 minus 1 is negative 5. Negative 2 minus 1 is negative 3. And I don't know if you've ever noticed, but there's a pattern going on here. Notice that these numbers are increasing by 2. And you could use it with the y or the f of x, where you're thinking about x going in and x being the domain. Okay, and so the x values go in and then the y values come out, which we know that's the range. Now, sequence notation is doing the same thing, but it looks very different. So what we're thinking now is, what's the first term? What's the second term? Or the third term? And now what's going on, it doesn't look like a table, but what we're saying is plug 1 in for n. So that'd be 2 times n is 2 minus 1 is 1. So the first term is 1. The second term just means plug 2 in. 4 minus 1 is 3. Now the difference is, over here on function notation, you can choose any x's you want. Well, for sequence notation, the first term is always 1, because you always just start with 1, 2, 3. You wouldn't say the negative 4th term. It always starts with the first term. And then if we plug 3 in, we'd get 5 and 7 and so on. But you still see the same pattern where the numbers are increasing by 2. So the notion of slope is not going away, being a rate of change. Let's do an example. Let's write the next 3 terms in this sequence. So what I'm going to do is I'm going to notice that the numbers seem to be going down by 5. So if I continue that pattern, I get 2, negative 3, negative 8. Here, let's see. I went up 3, but then up 6, then what might we do? Or maybe you would say multiply by 2 so that you have a constant rule that's doing the same thing every time. So that'd be 24, 48, 96. Now, I don't know if you remember this from geometry, but what we just used here is called inductive reasoning. And hopefully that sounds familiar. Inductive reasoning is just based on patterns or observations. Okay. So we used inductive reasoning here. Let's look at example 2. Let's write down the first 5 terms. So here, remember the first term, that would be a sub 1, means plug 1 in for n. So 3 times 1 plus 1 would be 4. 3 times 2 plus 1, 6 and 1 is 7. And at some point, you may notice a pattern, but you certainly don't have to use it. You can just keep using this nice, handy-dandy formula where you can plug in the 5th term. And the good thing about having a formula is that I can ask you what's the 100th term, and you don't have to list them all out. You can just plug in 100 and see that it will be 301. Whereas when you're doing a pattern like in example 1, you would have to list them all out. So there's benefits to having a formula. Let's look at B. If we plug in 1, 2 to the first power is 2, so we get 5. If we plug in 2, 2 squared is 4, plus 3 is 8. No, I didn't say that right. Plus 3 is 7. And now let's see if we plug in 3 for the 3rd term and then add 3, we get 8 plus 3 is 11. And if we go 2 to the 4th power plus 3, that would be 16 plus 3 is 19. 2 to the 5th power plus 3, that'd be 32 plus 3 is 35. So we have a formula that we can use. However, I do want you to notice that there's some patterns going on here, even though we didn't have to depend on them. Notice that we're increasing by 3, and you can see that slope is 3. That's the rate of change. Well, when you look here, it's not quite as obvious, but notice we went up by 2. We went up by 4, up by 8, and by 16. So there are some patterns here, but we depended on the formulas. Oh, by the way, this, without depending on the patterns, this is called deductive reasoning. Okay, and this is what we say is more concrete. And in math, we say that we're using maybe formulas, rules, theorems, postulates, and things like that. Okay, so deductive reasoning is more concrete, whereas inductive is a little more abstract. How many circles are in the seventh picture? Now, there's a lot of ways to figure this out. I'd like for you to pause and see if you can figure out how many circles there are in the seventh picture. Okay, now that you've returned, I'll show you a couple of different ways that you might want to go about it. You might want to make a list and say the first picture has 1 ball or circle, and the second picture has 3, and the third has 3, 4, 5, 6, and then maybe try to establish a pattern where you see we're going up by 2, we're going up by 3. So if I go up by 4, I believe that would have 10, so that would be 4, 3, 2, and 1. So indeed, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that's how the pins are in the bowling alley, huh? And so we went up by 4, and you could continue until, let's see, 1, 2, 3, 4, 5, 6, 7. And you could just continue that pattern and see what you get. This is one way of doing this problem. So I say there would be 28 balls or circles in the seventh picture. However, you could also notice that the seventh picture, if the first picture had 1 on the bottom row, then 2, then 3, and the fourth picture had 4, maybe you realize there's 7 here. 3, 4, 5, 6, 7. And that each row, so that'd be 6 and 5, 4, 3, 2, 1. So maybe you notice if you add these numbers, that will give you the answer. So let's see, that's 3, 6, 10, 15, 21, and 28. So that's another way to reach the same conclusion. All righty. Today, we're just looking at a brief overview of what you're going to expect in Chapter 8. After today, we're going to have some formulas that are going to help us to develop some things so that we can get busy. But before we finish today, I'd like to introduce you to summation notation, also known as sigma notation, because we use uppercase sigma, which is a letter from the Greek alphabet. Okay, this is uppercase, and usually the top and bottom are parallel with the little V here. So this is uppercase sigma, not to be confused with lowercase sigma, which looks nothing like uppercase. Okay, nonetheless, we're going to use quite a few Greek letters before the year is out, especially with trig. We use alpha and beta and theta. In physics, you'll use a few different things. Electronics, you might use some different stuff. You might use lambda or different variables in math and science. We borrow from the Greek alphabet. Alrighty, let's look at example 4. The number on the bottom tells you where to begin, and the number on the top tells you where to end. And I'll show you what I mean. I'm going to start by plugging 3 in for n. So that'll be 3 times 3 plus 1. Then I'm going to plug in a 4. So I'm going to start with 3. Then I'm going to count by ones until I reach the number on the top. You understand what I'm saying? Start with the bottom number, count by ones until you get to the top number. So now I'm going to plug in a 4. Then I'm going to plug in a 5. And then I'm going to plug in a 6. And I stop there because the number on the top tells you where to stop. So if I add all these up, that's 10. This is 13. 15 and 1 is 16. And then this last one, 18 and 1 is 19. So if I add these four numbers together, let's see, that's 23. Those two make a 35. That gives me 58. So, pretty interesting. That's how sigma notation works, or summation notation. And you see that it's a sum. It's a sum. Okay. By the end of this chapter, you'll be able to do something like, maybe n equals 1 to 98 of 5n plus 3 or something like that. And it won't take long. You won't have to add up all of those different numbers. I'll show you how to do it with a simple formula. Okay. Let's do one more to make sure you've got it. Okay. We start with 1 and we plug it in, then 2, 3, 4, and stop when we get to 5. So that'll be 1 squared minus 1 plus 2 squared minus 1 plus 3 squared minus 1, 4 squared minus 1, and 5 squared minus 1. And so it's a little time consuming. They do have a few nice calculators that will do this for you. 9 minus 1 is 8. 16 minus 1 is 15. And what is that? 24. Okay. And so we have 11 and 15 is 26. Plus another 24 is 50. All righty. And that's how that goes. Also, I'll even show you how to do something like this, where we go to infinity. So maybe we'll have something like this. Crazy stuff, but fun, fun, fun.